So let's look at this. What we do is, first of all, the first step is exactly the same as before. We look for a positive and a negative, which gives us an answer. So let's say we found one here, one value of x here that gave us a root there, and another value of x here that gives us a root here. So we know that it's somewhere between there and there. So well, we could use the bisection method and go halfway and see what that is. But what we do is we take the one on the right hand side of it, because we know it's somewhere to the left over here, and so I take this point here, I want it to be blue, found out the value of the function at that point, and then what I do is I use the fact that hopefully if I were to find the gradient of that line at that point and find out where that differential function equals 0, the gradient function in other words, with a bit of luck that will be nearer the root, and we can see from this sketch that it might well be. Okay? So that will give us our next guess. So rather than just going halfway, between here and here, we actually use the fact that the gradient of the curve might help us homing on that result a bit more quickly. So let's have a look at this for a sec. So if I had to draw on here the line, the gradient line here, and then complete this triangle coming down here like this. It's got a little triangle. And let's label this ABC. So we can talk about that triangle ABC. And let's call this x1, and this, x0, our first guess, and this x1. We know that the gradient is the line AB, how far we go up the y-axis, divided by CB, how far we go along the x-axis, like that. But the gradient is the differential of the function. If you think back to last year, that prime symbol is used to represent the differential of the function. The differential of the function. That prime means the differential. And we also know, by looking at this, that this length of this line AB here is actually just the value of the function when x is x0. So when x equals x0, fx gives us the length of this line AB, doesn't it? So we know that AB equals the value of the function. At x0, sorry. So AB is fx, 0 over CB which is the distance along the x part of that triangle, equals the differential of the function at 0. So that's a specific differential at x0 rather than the general differential there, which is how we find the gradient of the function at any point. Rearranging this, we get CB equals f x0 over f prime x0. Now, if we look at this, CB is important because CB is the difference between x0 and our new x1. So we can think of CB as being x0 minus x1. CB equals x0, our first guess, minus x1, which is going to be our next guess. So rearranging this for x1, because that's what we want, our next guess, x1 equals x0 minus CB. But we know what CB is, x0 over f prime x0. And x1 equals x0 minus the function at x0 over the differential of the function at x0. And that is Newton-Raphson's iterative formula. So this is Newton-Raphson. So if we look at it now, hopefully we can see how it can be useful. I have a guess, my first guess that I arrive at x0, so it's my first value of x. And then what I do is I find out what the value of the function is at x0. Then I differentiate my function and find out what the value of the function, this differential function, is at x0. Divide the value of the function at x0 by the differential at x0. Subtract that from x0, and I've got my new value for x1. So I'm not bisecting now. My next guess, x1, is picked using this method, which hopefully is going to zoom us in on this route a bit more quickly. If we're looking at a diagram, I think we can maybe see why it does. Okay. So that's the idea of it. So let's try that on the one that we've just done. Okay. So I'll stop this video here again. So this will be for Newton-Raphson, and then I'll give you a chance to try this new one on there, and we'll start it off together.